is the brain, energy, and depression. Now, today we've looked at depression before in one of the earlier broadcasts, and we looked at some of the possible factors and some of the most significant symptoms. What I'm going to talk about today is the role that energy plays in some of those symptoms. Now, I've said often in the blog that I left no stone unturned in trying to understand what's going on in major psychiatric disorders such as bipolar, schizophrenia, depression of various kinds. And because, what I found in my own experience with the mental health care system was and then subsequent research was the psychiatric pharmaceutical model was greatly wanting, and their chemical imbalance theory, which I'll take apart in a different broadcast, was greatly lacking in giving us an understanding of what's going on with all the symptoms involved in the various disorders. But today we're just going to have a look at and one of the things I discovered in my research, and I had some very good sources for this, was the role of energy, and specifically the role of mitochondria in creating energy. Okay, so this whole thing of energy, what we think of as energy is not quite what I'm going to be talking about here today. Related, but on quite a different level and scale, we'll say. And I think once I get through this broadcast, you'll have a better idea of what I'm talking about and why this would seem to relate quite strongly to many of the symptoms we experience. Now, I do have a 3-part series on my blog about this. That's called Bipolar, the Brain and Energy, and a little more specifically about bipolar disorder and the depressive phases of bipolar. But since researching and writing that a little over 3 years ago, I researched and wrote that in the spring of 2014. I've come to understand that the similar things are going on in just about any long-term chronic or even short-term case of depression, whether it's clinical depression, major depressive disorder, and even in some of the more short-term, so-called less serious cases of depression. Okay, so energy, what we think of as energy, actually, there's no one center for energy in the body. The stress response system can give us some energy fuel boosts in the form of various stress hormones, and I'll get to those towards the end. But what we kind of feel and experience of energy, it is actually the collective output of what goes on in the trillions and trillions of cells that make up our body, our organs, and our brain. And we have trillions and trillions of cells, 100 billion or so brain cells, neurons, and each one of those cells has their own little energy engine, and I'll talk a little bit more about this in a minute, but they're called mitochondria. That's what mitochondria look like, roughly, and I'll introduce these a little more detail in a moment. So what we experience as energy is actually the collective output of what's going on in our trillions of cells. And when it comes to mental states, cognitive function, and all that, particularly the energy created in our billions of brain cells. Okay, so now let's tie this, see how this relates to some of the symptoms we looked at in the broadcast on depression. Then I outlined some of the common symptoms and complaints, and I'm sure you can all relate to this if you experienced even a minor episode of depression. But like in the broadcast that I made introducing depression and the more serious long-term debilitating aspects of depression, we looked more at these, and we're talking about things like fatigue, and I'll explain these all a little more in a moment. Lethargy. I've got to make sure I don't misspell any of these. I'm kind of horrendous for that. What we kind of colloquially know as brain fog or brain freeze. brain fog or brain freeze. I'll get to that more in a minute. Anhedonia. Some of these, or almost all of these, anhedonia, I talked about in the initial broadcast on depression. Vegetative or catatonic states. Catatonic. And psychomotor retardation. Now, some of these, if you're just familiar with what I kind of refer to as garden variety depression, not all of this you'll have experienced. Certainly with most cases of depression, whether they're clinical depression, or major depressive episodes, or major depressive disorder, which is a chronic kind of a life-term thing. You'll certainly be familiar with fatigue, lethargy, and the brain fog. Anhedonia, certainly to a certain degree. These last three are more when we get into the really serious cases. And in the broadcast, the original broadcast on depression, I talked about the various factors involved: psychological, physiological, and where we go from just kind of a mood disorder into a really physiological disease model for depression. And what we're going to talk about today is where we're looking at the disease model of depression. Okay, now fatigue. I don't think I have to explain fatigue. It's just, just seemingly endless exhaustion, just never having the energy to do anything. Everything just feels like moving, like if you've ever been to the beach and you've tried to walk through waist deep water, it just seems like everything is slowed down and difficult, and it just never feels like you have enough sleep or rest. Lethargy related, just not feeling like doing anything, not feeling interested in doing anything. The brain fog, brain freeze. I don't know how many of you are familiar. I'm extremely familiar with this with my own condition, where it just your brain literally feels like it's not functioning, and like it just feels like it's not spinning a wheel, and some of the simplest tasks, like all of a sudden you just feel like you're frozen in time, and your brain just can't react to what's going on around you. If you're at home and kind of your day-to-day routine, this is disconcerting enough, but when it hits you, if you're at work or in public, this is going to cause panic attack, mental overwhelm, and breakdowns in itself, when your brain just can't function when you really need it to. And so what in a more technical terms, what we're looking at it is impaired cognitive function, short to longer term impaired cognitive function, and impaired memory function. And this is going to be really, really pertinent to what I'm going to explain today regarding energy in the brain. Anhedonia, as I explained before, is a Greek term, the inability to feel pleasure. Why can't we be happy? This sort of thing. That's kind of wrapped up in the term anhedonia. Vegetative catatonic states are kind of related to the brain fog, brain freeze, but kind of longer term. And again, I have enormous amounts of personal experience with this, where again, it just feels like your brain can't turn a wheel, and you're just kind of, just barely there. Like, we don't like the expression that the lights are on but nobody's home. This is more like you're home and the lights aren't on, like just nothing's happening, and you can just barely sit there and breathe. Really, really terrible feeling and experience. Psychomotor retardation is actual physical impairment. Again, this is more really serious long-term cases, but you even with shorter, less severe cases, you might notice where it just doesn't feel like even your body is reacting as it should, and physical movement feels restrained and difficult. Okay, so those are some of the symptoms that I'm going to I think our talk today are going to shed some interesting light on the actual neurological, physiological basis for these symptoms. And that should become, if I do my job well, that should become more clear by the end of the talk. Now, so mitochondria. As I say, we have trillions of cells, billions and billions of brain cells, and throughout the animal world, oops, I got to turn off my other computer here. Throughout the animal world, plants have a different way of creating energy, but in the animal world, energy is created by these little organa called mitochondria. And you have trillions of cells, billions of brain cells, and in every one of those cells will be up to several thousand mitochondria. And what mitochondria do, let me get this a little bit closer here. This is all, they kind of have this elongated shape, and there's these weird wiggly things that every illustration you see of mitochondria look something like this, and this just outlines some of the little chemical process that goes on. But what happens, what mitochondria does, I kind of liken it to the carburetor in your car. You have fuel, gasoline. Well, most cars use fuel injectors now, but carburetor is an easier thing to visualize. And the motor in your car can't utilize the gasoline unless it's converted into a vapor. Well, fuel injectors do the same thing, and that's how I think of as mitochondria. You have fuel in your body. You consume food and oxygen and energy reserves in your fat and stuff, and your cells can't create, they can't use that for energy unless it's converted. And what you see here is kind of the process for mitochondria converting the fuel, as it were, into energy. So that, in a nutshell, is what mitochondria does. And in a future broadcast on this, I'm going to try to get into this in a little more detail, because I think it's quite important to understand. And I'm freezing here again. well, I think you'll understand when I get through the rest of this broadcast why this is, I think, really, really critical to understand and know a little bit what's going on with all these little energy engines in our cells. So, all the cells in our body have mitochondria, and when you're using your muscles and those cells need to do their thing, the energy for the cells to do their thing comes from mitochondria. Now, all cells are really, really complex, regardless of how tiny they are. But as I've said in my blog and various posts, our brain cells, neurons, that complexity is taken to a whole new level. So I'm going to have, now, those of you familiar with some of my other broadcasts and certainly with many of the blog posts, you should be becoming somewhat familiar with the neuron. And so neurons, as I've quoted several neuroscientists, every single neuron is comparable in activity to a major city. And there's just fantastic amounts of activity that goes on inside a neuron. And the energy, again, for a neuron to do its thing is created, and you can see a couple of these are the mitochondria here. There's a couple depicted here, whereas in fact there are several thousand. And I'll explain a little bit more about mitochondria and how neurons function or not function in a moment. But, as I've explained about neurons before, they're like little tiny micro storage devices. All the details of all our memories and thoughts and things we visualize and the sounds we can hear, remember, we can hear in our head through memory. All the details of that are stored in neurons. And for neurons to do their thing, they have to connect with other neurons through axons and little tiny connections called synapses. Now let's have a little bit better look at a synapse. This is a synapse. So you have here, this is an axon. This comes from one neuron that wants to send along some information. And this is called this is the dendrite. This is the receiving end. So this is the sending end, and this is the receiving end. And this here is called the synaptic cleft, this little gap between them, mere 20 nanometers across, which is much, much thinner than even the human hair. And you can see these little dots in between there. Those are neurochemicals. When we learn about depression and various disorders, we get told a lot about neurochemicals, and it's all about neurochemicals. And I've got a couple of blog posts kind of taking that notion down a bit. Neurochemicals are certainly involved, but they're not the only thing going on. In any case, this is a synapse, and for neurons to communicate to each other, an electrical signal. This neuron gets all excited, sends an electrical signal down to other neurons. That electrical signal comes zapping down here, and you can see all these little sacs. That's where the neurochemical is. When it's not floating around in here, it's stored in these little kind of balloons here, and the electrical signal comes down here, stimulates these, and shoots some little neurochemicals over here, and that completes this little bit of transaction. You have in your brain about 150 trillion of these little connections, 150 trillion, which is literally an astronomical number. If we were to take a little bit of your neocortex, this outer layer of the brain, a little tiny cubic centimeter, there would be more synaptic connections, more of these little connections in that little cubic centimeter than there are stars in the Milky Way. It's mind-blowing. Okay, so this is critical to much brain function. These little, we get the neurons get excited, they send a little electrical thing down the axon, stimulates the release of neurochemicals. The neurochemicals send the message on to the next group of neurons, and this is happening within little bursts, hundreds of thousandths of a hundred thousandths of a second in duration, trillions of times per second for every moment you draw breath in your life. So needless to say, this is all rather important for your any kind of function, any kind of mental or even physical function, and I'll get to that a little bit more in a minute. Now, what is the role of mitochondria in all this? Well, again, I get into this a little more detail, on the blog and various posts, but and in my post on the neuroscience of music therapy, I've embedded a real cool little video, little short, I think it's 30 seconds or something, that kind of has an 3D artist depiction of neurons firing. It's kind of cool. But what will happen, and this is happening as you're listening to me, there's all kinds of activity going on in your brain as you're listening, and neurons are firing all over the place. When a neuron is going to fire, it has to reach a certain level of excitement called action potential. And that's when the electrical charge in a neuron builds to the point where it'll send the charge down the axon and cause that little neurochemical release at the other end. And again, this happens like literally trillions of times per second. So, and without getting into too much horrendously boring detail today, mitochondria, my whole thing is falling apart here. Mitochondria play critical roles in creating the energy for all this activity. Not only the activity within a neuron, and remember, there's like city level city, like the activity of a city going on in all of your billions and billions of neurons, and for it to send the message down to other neurons and to communicate and to coordinate all our physical movements and thoughts and everything that we possibly do in every waking and even non-waking moment of our lives. Neurons have to communicate, send these little mini packets of information to other neurons. And to do that, you have to create a certain level of energy in each cell, and that when that level of energy reaches a certain point, that's called action potential, and mitochondria are important for just the creation and maintenance of the information within each individual cell. But also there's this little part of the neuron where the axon connects. And this is really critical, what goes on in here for sending the electrical signals down. And mitochondria is critical for that function. Now, back to our little synaptic connection, if these neurochemicals, if they can't either be recreated, the the sort of the store of neurochemicals in these little balloons that has to be constantly replenished and manufactured. And that is why, you know, you can see here the end of each axon, these little kind of knobs at the end that connects to the other neurons, neighboring neurons, and other neurons in that particular group. The end is the energy to do these little functions is all produced by mitochondria. If mitochondria in some way aren't doing their job, this transaction's not going to happen, or it's going to be somewhat impaired, slowed down. And that is going to affect all the communication involved in a given neuronal brain network. Okay, now to give you, this is sort of the super micro scale of what goes on. Oops, and here's another little neuron. Well, we don't need that illustration quite so much. But I think, you know, some of you will recall, you know, that we have, you know, what connects all the groups of neurons, little brain nodules and brain regions is called our connectome. These are all long, what I call long distance wiring, long axons that reach all throughout the brain. And, you know, again, these electrical signals have to travel all these great lengths. You know, you know, if we look at our brain, you know, it doesn't seem very far. You know, it's only, you know, it's you know, 6 or 7 inches at most from one end to another. But in terms of you know, the scale of inside the brain, these are massively great distances. And some of the neurons, what we don't see here, some of these some of these axons travel down the spinal cord for great lengths. And this all requires electrical signaling, and that the energy for that electrical signaling is largely manufactured by mitochondria. So again, if all this electrical wiring, this, we'll just call it electrical wiring, if that's not carrying signals, then brain functionality, and we're talking mental, memory, cognitive, physical functioning, is all going to be slowed down and impaired. And again, that comes back to mitochondria. So now that should give you, hopefully, a little better picture of what energy, you know, what we experience as mental or physical energy. Now, you know, it's hard to put this into context, what exactly this means. But if we come back to some of our symptoms and we try to keep in mind what I just explained, you know, if neurons can't communicate with each other, if, you know, large bundles of neurons, little neuronal regions and brain nodules that create everything to do with, you know, our emotions, our thoughts, our ability to react to life, our ability to take in visual and auditory information, that requires enormous amounts of neuronal activity. Every move we make, every thought we have, all requires enormous amounts of neuronal activity. And this process I kind of very briefly outlined here. Now, in my research for the 3-part series on my blog, I came across a great deal of evidence for mitochondrial dysfunction. as a role, as a factor in the depressive phase of bipolar disorder. A lot of the research I looked into was specifically about the depressive phase of bipolar disorder. But since, as I mentioned, since doing all that research and writing that series in the spring of 2014, I've talked to a great number of people, you know, are having all these similar symptoms to varying degrees of severity and time duration. And so I started looking into those kind of cases as well, and just found a remarkable number of similarities. And it just made a great deal of sense that while the pathology, you know, between bipolar and other disorders such as depression and anxiety disorders are somewhat different, and some different factors involved. While the pathologies are different, they kind of lead to the same path. And mitochondrial dysfunction would seem, you know, I can't say with absolute certainty, but boy, a lot of the evidence just really stacks up. And if we, you know, I just tried to really briefly outline it today, and in future episodes, I'll try to get to it in a little more detail with a little more evidence. So we have mitochondrial dysfunction as a possible factor in many of these symptoms. So briefly, you know, what causes this mitochondrial dysfunction? Why are these little energy engines in our cells not doing their jobs? And so this is something I looked into in some detail. And I kind of boiled it down to 4 possible avenues. One is simple exhaustion. Oops. Simple exhaustion. You know, this is like, you know, this is kind of cellular biology 101, as I said in the series. You know, the fuel and all these functions are not in finite supply. You know, just everything is limited. And, you know, if you overtax something, you know, any kind of working organism, if you overtax it, it will break down from exhaustion, and the supplies, you know, the fuel supplies and everything will just kind of run out and break down. Now, when I look at, you know, certainly with bipolar, and this is where the pathologies are a little bit different between bipolar and other disorders. But when you know, in bipolar, you have long episodes of mania where everything in the brain and, you know, people are fired up for great lengths of time. And this is where this kind of literal exhaustion comes from. But when I look at other cases and some of the background, you know, I can look at life events and what's been going on prior to the episode of depression hitting seemingly out of the blue. And I can see circumstances in that person's life and brain activity required to deal for that would lead to a similar level of exhaustion. Now, more kind of cellular biology 101 is we can, in a cell, we can get a buildup of toxic waste. Explain this a little bit more in the next episode. But every cell, and again, this is kind of Biology 101. You know, you take in fuel, that fuel is converted to energy, and there's going to be a waste byproduct, just like your car. You know, if gas goes in one end, it's great energy is created, and the waste product is vented out the exhaust pipe. And all cells have that same process. The fuel comes in, it's converted to energy, and there's a waste byproduct that has to be vented or exhausted, sent out the other end. And this is where sleep becomes really important, because it turns out, you know, in the brain, there's all kinds of little cells that have all kinds of different jobs, and there's special cells and special little brain systems for whisking away this waste. But there's a good deal of evidence that the downtime, the mental downtime and the physical downtime of sleep is necessary for these little janitors, I call them, these little brain janitors, to go in there and whisk away all this you know, exhaust waste. And so if sleep deprivation is an issue, and it almost always will be in most cases I look at to some degree or another, sleep deprivation is going to cause problems with how all our little individual brain and body cells dispose of the waste product that's produced just in the normal cell functioning. Now, great interest to me, and I have some terrifically good resources for this, is chronic stress. Now, when we need energy, often that comes in the form, you know, especially short-term energy, it's going to come in the form of stress hormones. You know, this is what stress hormones are designed for. Give us those little bursts of energy when we need them. But all of these were designed for short-term bursts of energy. And there's kind of an interesting, weird neurophysiological difference between good stress and bad stress that we can't get into today. In either case, chronic stress will have chronically elevated levels of stress hormones, and there's some very good evidence that these stress hormones in chronically elevated levels are going to damage and burn out mitochondria. Mitochondria. Okay. And lastly, in this one, I can't say I know a great deal about oxidative stress. This is kind of a weird one to me. But this, again, is just part of the normal function of any cell. And this is kind of more related to the aging process. But there's this whole concept called oxidative stress, which can burn out or damage mitochondria. So we have these 4 different possible avenues for damaging all these little energy cells in our brains and bodies. And you know, one of the things I've kind of thought about and looked into is, you know, the possibility that people who are particularly prone to the symptoms, the more severe and prolonged symptoms of depression, you know, is it the mitochondria have been burned out by these, you know, various life circumstances and things going on, or maybe there's some kind of genetic pronation to somehow weaker mitochondria. Mitochondria always regenerating themselves. So there's possible something's not right in that regeneration process. Either way, in any case, I think there's an enormous amount of evidence for what's going on with a number of our symptoms being on account of mitochondrial damage, mitochondrial dysfunction. And I'm going to leave that off for now. And this is just an introduction, and I'll try to get into this in more detail in future broadcasts, okay? So I hope that was informative for you. Thanks for joining me, and we will see you again soon. Bye now.